Okay, so you give me this table, right? The top start is finding the speed. Then how do you find the energy? So let's find the speed of this individual one plus individual. So if the given meters in 9 minutes, how many minutes? The given meters in 9 minutes, right? 9 minutes. We want to find the speed, which is change it to 1 minute. So all we need to do is the given divided by 9. I don't have a calculator. All right. But it should be a decimal, right? That's 3.5. Yes. Oh, this is good. So did you right? It's a figure, right? Yes. Okay, so this is your speed. Inverse of this. Do you guys understand it? Oh, by the give me a value of this. No, 9. Okay, you guys understand this? Okay, so I think that so if they rent the meters, 9 minutes, so they've been running. This is this, then.
Nice of you.
Last month, the invoice doesn't have, so you cannot pay.
It should be sent to your dad already. Don't have. Okay. I can ask that man to send to him again. Okay.
How much you write in one minute? How much to write in 1 minute? Especially writing.
Oh, done. Okay, good. Okay, good. Dylan, that is singing. Singing, that's Dylan. Okay, come, let's take out your notebook. Singing, try to copy the notes as you go along. Okay. Dylan, how was your test? How was your test?
24 out of 30.
24 out of 30. Okay. Sabrina. Okay, yeah.
But like others mistake.
Ah,
Yeah.
okay. But was there enough time to finish it? Yeah. Okay, come.
And then divide by 2 equals your average. My average, yes. So you take 2 of
Let's do a quick recap of last week's stuff. Sabrina, how many types of bonds are there that you need to know? What are they? Covalent, okay. Okay. And that stands for? All right, so 3 types already: covalent, ionic, intermolecular forces, and lastly, okay, just metallic bonding. All right, singing, take note, there are 4 types of bonds you need to know. and as I said, only for this one.
Yes.
All right,
That's good. Okay.
Dylan, when do you know it is a covalent bond?
It's a two or more non-metal.
Okay, simple as that.
Yeah.
You see, two. Okay, let's take the two. Two non-metals bonded together. That bond is a covalent bond. That one is super important. Don't miss that out. So when do we find ionic bond, Dylan?
Metal and one non-metal.
Okay, again, simple as that. You see one metal and one non-metal, then that is an ionic bond. Where they are linked. So yeah, very simple, but you tend to miss it out. Try not to. Now, metallic bonding only in pure metals. Okay, but let me be very clear. So there are two kinds of metals. This one we gone through last week, either pure elements or alloys. So these two are considered metals and they have metallic bonding. Sabrina, where do I find intermolecular forces? Okay. Okay. It's in between covalent molecules. All right, maybe I add in that word in between. All right, simple covalent molecules. You tend to find intermolecular forces. Now, I think as the word implies, inter means between. Molecular, of course, refers to molecules. But in this case, we are interested in simple covalent molecules. All right. One other thing that I think I emphasized last week, anytime you see the word molecules, it is definitely involving covalent bonds. All right, covalent bonds are present anytime you see the word molecules. So don't use this word lightly. Molecules must contain covalent bonds. But what if my compound is ionic? It contains ionic bonding. I technically can't use the word molecule, no. So for example, your favorite NaCl. This is an ionic compound. So I do not call this a molecule. What is the word I use for this?
Yeah.
Yeah. So all of you take note. This is an ionic compound. Do not use the word molecule. Maybe in lower set you can do that, but upper set you can't. So we call it NaCl for formula units. This one, metallic bonding. Well, you don't use the term formula unit. You don't use the term molecule either. Right? There's no particular description for that though. So you leave it as it is. All right, Xing, any questions? No? Oh, good. No, because for me, I try to follow the textbook order, even though your school may be skipping around the chapters. Are you in the same class? Oh. Oh, okay, okay. All right, so anyway, my point is, I'll be following the textbook order. But of course, if you think you want to ask me anything else, yeah, definitely free to do so. All right, so now we are currently still in chapter 4. But I give you an overview. This is actually a broad, very, very broad overview of chapters 4, 5, and 6. Now let's continue with ionic bonding. One question. Let's say, oh, any questions? Dot first later. No. Fine, Sabrina, fine. So what if I give you something like this? Okay. Magnesium carbonate. How does the formula look like? Or I mean, are you even familiar with the formula? It's magnesium carbonate. Oh, what's the formula for carbonate? Have you all gone through that? Oh no. Okay, then I shall go through. Okay, now come, let's go back to this part here. Sorry. It is. But the thing is, you need to know the formulas, otherwise it's quite hard to go through chapter 4. So maybe that's why this teacher decides to start with chapter 6. But nevertheless, I think this is important. Anytime you know that something is a salt, it is an ionic compound. Or if the question tells you that it's a base, it's 100% an ionic compound. But I didn't mention what are salts. Or even for the matter, what are bases? Okay, for salts, is in another chapter, I think chapter 7, but I'll give you a clue right now. In fact, you should write this now because sooner or later you need to know about it. Okay, salt. Simple definition. It has a cation and anion. Come, Sabrina, which one is positively charged? All right. Okay, I'm not going to write it down. I assume you all shouldn't have a problem with that. Now, as I said earlier, it's definitely an ionic compound. And obviously, it contains ionic bonding. Now, let's be very clear. Where is the ionic bonding? Or where is the ionic bond? It is between cation and anion. Now, simple salt, sodium chloride. Dylan, which one is the cation? Okay, guys, important. I've done it last week, but it's always good to remember. Metals tend to become cations. Remember metals, what do? They like to lose electrons. Okay, basic stuff. Yeah, remember that. Serious. But obviously there'll be exceptions, so we won't touch on them. And of course, the reverse is true as well. Non-metals, they tend to gain electrons. So I think in this case, it's quite straightforward. Sodium is the metal, chlorine is the non-metal, so therefore you have this. Now, occasionally, they can also write an arrow here. It's possible. Right, so to make things easy, essentially, where is the bond again? That was my question, right? I have sodium cation. I have chloride anion. So there is this bond in between them. This is the ionic bond. But what exactly is an ionic bond? Now, essentially, you will be asked to describe it sometimes. It is, okay, try to follow the words. Strong. You need to include that word in. Electrostatic attraction. Again, let me remind you, cation is positive, anion is negative, so they are opposite charges. That is why they attract each other. Even though at your level, they probably won't ask about this. Okay, opposite charges attract. But I think the concept should be quite easy to understand. But let me emphasize, in case you're asked to describe ionic bond, your teacher wants to see the word strong. Electrostatic attraction. Better still, it's actually a whole phrase between cation and anion that describes your ionic bond. Okay. But things are not that simple, unfortunately. Do you think your sodium is going to be alone? Do you think your chloride is going to be alone? It's not. In other words, I will have other chloride anions around too. Okay, I may have one here, one here, one there. Okay, these two are not just by themselves. They are surrounded by other ions too in a certain pattern. So you don't need to know the pattern. And therefore, there's also an ionic bond here, here, and there. Okay, so keep that in mind. An ionic bond is not just between two ions. It's between one ion and other opposite ions. So normally you won't be asked to describe it, but just keep this model in mind. Okay, each ion is surrounded by other ions. Maybe I just put down this point here. So therefore, you have ionic bonds all around. It's not just one single ionic bond. Okay, so keep this model in mind. Now, guess what? My chloride is not alone either. It's also surrounded by sodium here, sodium here, sodium here. Okay. Now, there's a fixed pattern, but like I say, at your level, no need to know that pattern. So guess what? I have an ionic bond here. Remember opposite charges, positive, negative, positive, negative, positive, negative. So ionic bonds are all around everywhere. So that means, when does it stop? It doesn't. Ionic bonds occupy your whole piece of crystal. As long as you have a solid piece of crystal, the whole crystal is ionic bonds. Okay, so that is important, and therefore, we should not use the word molecule. because it's not just sodium and chloride alone, no. They are packed all over the place. They are bonded all over in the whole piece of crystal. Right, so do not use the word molecule, use the word formula unit to represent ionic compound. Oh, one more thing. Oh, since you've done chapter 6, what do they call this structure? Such a big structure. Oh, okay. Never mind. Then write down. Because as Sabrina pointed out, it is stretching throughout the whole piece of crystal, no? So therefore, that's the name for it. We call it, oh, you better know. Okay, fine, giant crystal lattice, but that's okay, that's okay. But let me use a more specific term, giant ionic structure. Later you see the reason why I use this term, even though giant crystal lattice is not wrong, or giant lattice is not wrong. Okay, so the bonds will be stretching throughout the whole piece of crystal. Giant ionic structure, giant crystal structure, that's fine too. Giant ionic lattice, giant lattice. But again, as I said, I use this more often for an important reason. Okay, before I go too far off, let me come back to this salt again. So what is a salt then? I haven't totally answered the question yet, no? So for example, what if I tell you this one? Is this a salt? Or what is this anyway? Anyone recognize this? Oh, never mind. This is sulfuric acid. And the name already tells you it is not a salt. Okay, so this is not a salt. Huh? Magnesium carbonate. Is this a salt? Okay, in this case, yes. All right, this is a salt. So, without going into too much detail, I'll just tell you in very simple terms what is a salt. Okay, very simple. For now, all you need to know what is a salt. A salt contains a metal. Now, obviously, this metal is in the form of a cation. And there is something at the back. You need an anion, obviously. For now, you will restrict yourself to this field. If this is a chloride, sulfate, nitrate, carbonate, for now.
Yeah, this is.
There are many others, but this will be the 4 basic ones. And you also need to know the formula. Chloride, you have seen it, Cl minus. Sulfate, SO4, remember the charge, 2 minus. Nitrates, NO3 minus. I will ask you about the formulas every time. Okay, carbonate, CO3, 2 minus. Okay, can. But let's go back to our good friend here, magnesium carbonate again. All right, so as I said, this is a salt, magnesium carbonate. But question, where is the ionic bond? Between what and what? Okay, this one try to visualize it, or let's try to understand it. Now, essentially, find out who is my cation. Magnesium. Oh, what's the charge here? Which group is magnesium in? Good. How many electrons can it lose?
2 electrons.
2, so it's 2 plus. That's how you don't even need to draw it out. Group 2 means it can lose 2 electrons, so it becomes 2 plus. Carbonate, I already given you CO3, 2 minus. And therefore, my ionic bond is right between these two guys. And so that is where your ionic bond is in between magnesium cation and carbonate anion. But as I said earlier, I need to remind all of you, it is also bonded to other opposite ions. So there will be other ionic bonds as well between, basically just between these two, magnesium and carbonate. But they are all over the place. But there's one small question, right? Does anybody want to ask? How about this guy? Carbonate. What is carbonate? You have 1 carbon, 3 oxygen, right? How are they bonded then? You must have 1 carbon atom and 3 oxygen atoms, huh? But how are they bonded, Dylan? Ask first, ask yourself, are they metals or non-metals? Okay. Yes, that is the important thing. In other words, in between this, they are actually covalent bonds. In fact, 3 covalent bonds. And the whole thing is charged. It's 2 minus. So very simple. If you see something like this, magnesium carbonate, make sure you know where's the ionic bond between cation and anion. That is the ionic bond. But within the anion itself, I have covalent bonds. All right, so magnesium carbonate essentially contains both ionic and covalent bonds. That is the important thing that I want you to know. Lastly, so magnesium carbonate, is it still considered an ionic compound? Answer is yes. Guys, even though I say that it contains both ionic and covalent bonds, it is still an ionic compound. We still call it an ionic compound because it's the ionic bonding that dominates. Remember, it's a giant ionic structure. And I want you to add in, anytime you know that something is an ionic compound, it always has a giant ionic structure. Always, no exceptions. No exceptions. All ionic compounds have a giant ionic structure. All. In other words, all salts have it. Because all salts are ionic compounds. Just a small note, even though you don't really need to know this. Good news. Notice I didn't draw any further. For you guys, you will not be asked to draw the dot cross diagram for this one. Okay, because it's not so straightforward. No, it's not a simple diagram. Right, so I didn't ask you to draw the dot cross diagram for this. Okay, questions, anyone? No? Fine. Okay, just one last thing for actually a few more things. Remember that time what did I say? Oh, singing, you need to copy. Done? Done. Huh? Now remember ionic bonds, I told you that all salts are ionic compounds. All bases are also ionic compounds. But I didn't mention what are bases. Mhm.
Like,
Yes. What did they contain?
huh?
Okay, come, guys, write this down. Even though there's another separate chapter on it, but at least I want you to know it. Now, just now I said that salt is matter plus this anions. Okay. Now, a base is very similar. So a base also contains a cation and anion. Obviously, it's an ionic compound. I think I made that quite a few times. So base is an ionic compound. Right. Again, you know, the same story goes. Ionic compound means ionic bonds are present. It also means it has a giant ionic structure. But what's the difference there? Now, try to follow. The cation is a metal too. But the anion, there are only two possibilities. Either it's an oxide or hydroxide. There are only two possibilities for the base. Formula-wise, oxide is O. Sabrina, what's the charge for oxygen? Which group is it in? 16, right? Group 16. So how many electrons can it gain? Thinking, how many electrons can it gain? Yeah. All right, because it's in group 16, it can gain 2 more. to give you the full shell. So therefore, oxygen will form oxide, which is 2 minus. So whenever you see the word oxide, it means it has already ionized, become O2 minus. Hydroxide is this formula, OH minus. Okay, fine. Right, so examples, very obvious ones like okay, let's say magnesium hydroxide. Magnesium is a metal, hydroxide is the anion that makes a base. All right, so basically this is a base. So once you know it's a base, the same thing applies. It's an ionic compound, it contains ionic bonds, it contains giant ionic structure. Top magnesium formula Mg2 plus. Hydroxide, I given you earlier, OH minus. Dylan, what is the overall formula of magnesium hydroxide? Uh-huh.
2 plus.
Uh-huh. Now the thing, I think your school may use the cross, but I don't like to use the cross. Okay. So Mg is 2 plus. OH is 1 minus. Remember, don't write the 1 there. Okay. You just don't like to see the 1, just minus. So what's the LCM? Well, it's 2. So for 2 plus, unchanged, just times 1. OH is 1 minus times 2. Matter comes first. So make sure write the matter first. But I want all of you to pay attention. OH you need to times 2. How do I write it then? I have to include a bracket. Don't forget the bracket. And 2 is the subscript. Okay, so that is your formula. So just to be very clear, let's say you manage to get a crystal of magnesium hydroxide. You can even see the crystal with your eyes. One large crystal. I mean, of course, there are many ions inside, but what you need to know is this. Magnesium ions to the ratio of oxide anions is always 1:2. Just keep that in mind. I don't care how big that crystal is, the ratio of these two ions will always be 1:2. One quick recap. Where's my ionic bond? Well, still the same. It's between cation and anion. But like I say, you have other bonds around too. Okay, I'm not going to draw it out anymore, but just keep this in mind. The ionic bond is always between oppositely charged ions. Oh, of course, this one also has other ionic bonds to other magnesium ions. Again, let me re-emphasize. If I isolate OH minus, you have the O atom and the H atom in between these two. Singing, what's the bond in between these two guys? Here, that would be your covalent bond. Okay, so just keep that in mind. Reminder, H is non-matter. Even though it's on, if you look at your periodic table, H is closer to the side of the metals, but is considered a non-matter. Right, so therefore, O and H, they have covalent bond in between. Okay, because O and H are both non-metals. Questions, anyone? No? Okay. Okay, just a few more points. Let me see. Where are my notes? Okay, let's just finish it off. So ionic compounds. There are a few things special about ionic compounds, and they like to ask about this. So ionic compounds, they tend to have, remember, strong electrostatic attraction. Therefore, they have high melting and boiling point in general. Okay. Ionic compounds tend to have high melting and boiling points. Actually, two reasons. The first one is because ionic bonds are strong electrostatic forces of attraction. The second reason, they have a giant ionic structure. Okay, so this is a super common question. It's almost like a free marks for you. No? Explain why do they have high melting and boiling points? But can I just add one word? Strong electrostatic attractive force. They like to see the word electrostatic there. So just to give you an idea, it looks somewhat like this. Right? Oh, by the way, chlorine ion is quite big, sodium is smaller. So they are all joined up, no? Imagine this is a solid. Remember solid, Sabrina? How do the particles behave in a solid? All right, they vibrate in fixed positions, regular pattern, orderly structure. So they basically cannot move too much. So if I want to melt it, what do I need to do? I need to weaken all these bonds, no? All of them. And remember, all these are strong bonds. So that is why it's very hard to melt it, because you need a lot of energy to weaken all these bonds. So therefore, I want you to add one more thing. Let's go back to my statement here. Especially for a 3-mark question, then you want to add one more point, right? Lots of energy is needed.
You go, you have two speeds, right? You take the same speed, you add that up, there's your total. Your quantity is how many options you have. So that's two speeds. 6 divided by 2 equals to the average speed. Okay. I always do this.
Aspect rules. A little bit of the learning of such a calculus.
In the case of boiling, you need to break them totally.
You know when you get sugar, yesterday it's like at the same time.
What the horror movie we can totally hate the book, especially the class of this one.
It's just a small note, even though they normally won't be so particular. I use the word weaken because this is more applicable to melting. You don't totally break the bonds, right? For melting, because the liquid still has the bonds there. Oh, yeah, sure. But if you want to boil it, then you need to break all the bonds. And obviously, it's going to need lots of energy. Okay, so just add this in case you're ever asked, why do they have high melting and boiling points? Okay, questions? No? No? All right, just a few more things. Ionic compounds. Oh, by the way, have you come across the term physical properties? Physical properties. Like what? Yeah, what do physical properties mean? Oh, okay. Okay. Examples of physical properties? Okay, that one may not be so no. You must write down now because you're going to see this term for the rest of your upper side. It's definitely going to come up for other chapters too. Now, physical properties are what you have learned, especially in primary school or even lower secondary densities, right? Yes. Color is a physical property too. State of matter, even though it's temperature dependent. And I want you to highlight this one, melting and boiling point. Highlight it. Anytime you're asked about physical property, think about this first. But more than that. Electrical conductivity. Now, even though less often asked, heat conductivity too. Okay. Yeah, Dylan, take note of this physical properties. You'll definitely be asked about this in other chapters as well. Now, in contrast, your question may also ask you about chemical properties. In the simplest sense, it means the chemical reactions that the substance can undergo. Okay, just keep this in mind. Yeah, of course, you may forget it, but I will keep reminding you. Now, what else? Okay, examples. Flammability. Well, as the name implies, it tells you how well the substance burns. Reactivity. How reactive it is. And occasionally, or in some cases, pH. pH is quite a bit gray. Some people classified it as a physical property, but to me, I think it relates more to its chemical nature. Oh, but for pH, I want you to be aware it only applies to aqueous substances.
I just want to
Sabina, fine. Right, let's finish this off. So okay. Let's just finish this off. Ionic compounds. Now, I'm more interested in this case, the physical properties. Okay, so we have already established high melting and boiling point. Oh, I forgot one important one. Can you guys add in just now physical properties? Solubility in water. Sorry,
Is it water?
is it water only? You want the L one? Okay, also can. But that one doesn't come up often, even though it does come up occasionally. Besides water, Sabrina, what other solvents are there? Yes, good, alcohol, but alcohol, I'll just lump it as an organic solvents. So take note, yes, occasionally alcohol may come up, or some other organic solvents. All right, I'm not going to explain the word organic until much further down the road. Okay, come. Two. Okay, many are soluble in water. Notice I use the word many, not all. Further down the road, you have to remember which are the ones that can dissolve, which are the ones that cannot dissolve. But for now, just many. Okay, but however, I want you to know this. So let's say this is sodium chloride. It exists as a solid salt, obviously. But once you add this to water, what happens is going to ionize. it breaks up into ions. So this is what I call ionization. Here S stands for solid, but importantly, what state do I put here? No, highlight this. They are now in aqueous state. Now, obviously, this process is also known as dissolution. Okay, once it dissolves, this okay. The key point is this: once an ionic compound dissolves in water, it forms the two ions. It breaks up into the two ions. Give you one more example. How about this? Let's say I have. Okay, this one should be quite straightforward. Oh, by the way, this is called calcium hydroxide. You can buy it as a solid. But you dissolve it in water, you get this. Now, I want you to be careful. There's a 2 here now. There's a 2 there, which means I have to put a 2 there. Notice the 2 is no longer a subscript. Here, the 2 is not at the bottom anymore, and it's now a coefficient. So this is the thing a lot of students will get wrong initially. Do not write it as a subscript on the right-hand side. Oh, of course, you can write in. This is also called ionization. This is also called dissolution. Oh, one other thing. Important. Once they become ions like this, once you dissolve in water, these ions are free to move. It is somewhat like a liquid already. Okay, so once you dissolve in water, the ions are no longer locked up in fixed positions. The ions are free to move. And that means what? It means it will lead to my third physical property. It can carry an electrical current. Meaning what? They are electrically conductive. Oh, by the way, electrical current Well, you haven't learned it in physics yet, or maybe you have last time in lower sec. Basically, it's the movement of charges. All right, so just to make your notes complete, I'll put number 3 here. Okay, so aqueous solutions can conduct electrical conductors. And of course, to explain it, well, you use about the same words. Oh, questions, please ask. What if it's a solid in its pure form? Solid ionic compounds. Can they conduct electricity, Sabrina? Do you try using salt to conduct electricity? Solid salt. Cannot, cannot. All right, so I want everyone to be really clear. As a solid, they cannot do so. Once they are dissolved in water, yes, they can. Salt water can conduct electricity. How about this one? Xing, what does the word molten mean? Okay, must know. Dylan, molten? Yes, good. It's melted, meaning it's in liquid state. Yes, please try to remember this word molten. You will definitely see it here and there. So the last part, molten ionic compounds. How Sabrina can conduct electricity? Yes, good.
About page 23.
I don't think it has any information.
But
Keep 4 and 5 in mind. They like to ask about this, compare and contrast about electrical conductivity in ionic compounds. Oh, anyway, I didn't explain right. So basically, let's say I have sodium chloride again. So we can write something like this too, sodium chloride as a solid. If you melt it down, well, of course, it becomes a liquid. I mean, you can write this if you want to, but it's more than that. The ionic bonds weaken. And the ions are free to move. That is the key point again. And that, of course, comes back to the same conclusion. They can carry a current. Okay, questions, anyone? No? All fine? Okay.
I'm ready to leave support. I want to. But. Bookie is the machine. It's a one in the vendors. I. That's great. That's huge, very complicated. Right. Yeah. That's high feedback. It never is. Oh, but it does. What the unit for this here, right? Okay, please. Yeah. There's a couple for sure. He's kind of taking him there. No. All right. How did this? Those are doing. Bring some things. Who's echoing? This echoing your home. Yeah. Yeah, break chance echoing. Oh, pretty already calling. No. Echoing is all that. This is supposed to be. I guess the bridge is for the business.
This one is it? The ions Mg2 plus and CO3. Two minus form the ionic compound Mg2CO3. Yeah, why is it wrong? Yeah. Yeah. Yeah.
Yeah, sure, sure. That's fine. Basically, like, I think it's shopping, guys. I'm trying to, yeah, something in the middle. Yes. Ah! You just. I'm not answering that question. I can answer the question. How do you miss interpretation? Do you have what? How is what is God within in our face? How is this insignificant? Watch. More than this. It's much more. Okay, guys, last question. How much travel sensitive? How to go to this, how far can you travel to far? It's all very fast. Maybe 5 per hour. So this is 1 hour. Wow, it's just right? Someone can say, no, can you okay, good luck. So basically, it's like, towards it per hour, right? It means it's like 1 minute. So it means it's 1 hour. You want to find more comfortable going 4 hours, that's something. Emotional. Once. Once also, especially
Start.
guys.
Now, guys, Sabrina is asking about this question. Yeah, of course, it's a difficult question, but I expect it to come up occasionally. Okay, guys, first thing first, look at this formula. I hope you notice, do you see a matter inside? Thinking, do I see a matter? Yes, good. The rest are all non-matters. So therefore, you should be able to deduce this is an ionic compound. So that's the first thing. Now, second thing, obviously it contains cation and anions. So in other words, it's not just one cation and one anion anymore. It can have more than one for each of this. So first thing first, magnesium. This one you should know. What's the charge for magnesium, Sabrina? Group 2. Yes, you can safely say that it's 2+. Now, at the same time, I hope you notice, what is this, Dylan? OH. Yes, good. OH is called hydroxide. Guys, you need to know the name. And of course, it's written as OH minus. Now, in this question, they're interested in S silicate. Okay, I can't even pronounce it. Si4O10. So therefore, if I want to split this out, what do I get? So I can write something like this. It's made of ions, so I have 3 magnesium 2+. Okay, and 2, guys, take note, I'm no longer using subscript. My 3 is now a coefficient here, 3. Now, likewise, I'm not using a subscript here, it's a coefficient now. And 1 silicate ion. No need to know the name, but it's a silicate unknown. Okay, unknown. Unknown charge. So how? Well, you can do your algebra. Notice the whole thing is what? The whole compound is neutral. Overall neutral. Okay, so form your algebraic equation. 2, sorry, not 2, 3. 3 times plus 2 plus 2 times minus 1 plus x equals to 0. Okay, so 3 is from here, 2 is from there, plus 2 is from the charge, minus 1 is of course the charge. So solve for x. Right, what should you get if you solve for x? Okay, you should get -1. Okay, you should have your answer now. Keep this method in mind, it can come up for you. Can try to highlight it if you want to. It can definitely come up for you for your questions. But tell you what, let's at least go through the fill in the blanks. I need everyone to get them right. Right. Okay, come quickly go through, Dylan. Yes, obviously your spelling must be right. Sabrina. Okay, positive or positively charged, that's fine too. And obviously this will be the opposite, negative. These are all really basic stuff. Singing. Okay, strong electrostatic attraction, or if you just put electrostatic, that's fine too. But it's good to remember that word strong in front so that you can remind yourself. Right? This one, Dylan. Yes, of course, I mentioned that all the time. This one, Sabrina. Giant ionic structure. Of course, you can also substitute a giant lattice structure, but I don't use that for a reason. I'll tell you next time. Okay, so either one is fine, but I personally prefer giant ionic structure. Singing. Okay, melting and boiling points. Dylan. Insoluble in organic solvents. So by right, ionic compounds do not dissolve in alcohol. Okay. Sabrina. Good. Or Sabrina. or soluble. Let me be a bit more grammatically correct, or dissolve in water, but not in the solid state. And try to get all this right because these are the basics. Let me just finish off the true and false. Singing A. What? Oh, do you know what's an octet? No, right? Octet, it doesn't come out all the time. It means 8 electrons in the valence shell. Okay, octet means 8 valence electrons. Eight valence electrons. Now, contrast this. Nowadays, they don't use this word that much. Contrast this to the other word, duplet. Duplet means 2 valence electrons, but there's a qualifier. 2 valence electrons is the only shell. So, guys, I want you to be careful for A. The answer is false. Because what is the first noble gas, Sabrina? Helium only has 2 valence electrons, right? So it cannot have an octet configuration. So the exception is helium. Okay, B, Dylan. Because they don't become noble gases, they just become ions only. Okay, they do not become noble gases. They only achieve a noble gas electronic configuration. C, Sabrina. In general, true. Yep. D, Singing. True. E, Dylan.
False.
Why?
The food ring exploded away. Sometimes take the training races. You're not. You open it out. Go and spend.
AlCl3. Now, I want everybody to be very clear. It already tells you this formula unit has only one aluminum cation and 3 chloride anions. So it's not 3 aluminum and 1 chloride, it's the other way around. 1 aluminum and 3 chloride because of the subscript 3. Okay. F, Sabrina? Yeah, false, of course. Again, same thing, make sure you can tell, but write it out anyway. Because these two are equally charged. 2 plus versus 2 minus, they are balanced. So I only need one of each to form this formula. Only 1 magnesium and 1 carbonate. I don't need 2 magnesium then. Okay, this is the wrong part. I don't need 2. Okay. Right, G, Singing. In an ion lattice, okay, once you see the word lattice, it means giant lattice structure. The ions of the same charges are arranged side by side. Okay, this one is tricky. What did I draw just now? Did you notice? Did I draw them side by side? No, I didn't. Because you need them to be opposite to express. Now, even though this is not likely to come up, but imagine you have like this, what will happen? Cl minus, Cl minus, Cl minus. You're going to have a big problem. Yeah, it's going to be recursion instead. Even though this is not likely to come up. You won't have attraction anymore. You have repulsion instead. So the whole structure will just fall apart. So just take note of this. Okay, so you can't have similarly charged ions side by side. You can't do that. Likewise, I can't have sodium side by side. Again, repulsion will occur. Okay, like charges repel each other, even though they won't ask this in chemistry. Okay, I think the last one is last true or false. Yeah, Dylan, last one.
False.
Obviously, they are strong. They have high melting and boiling point, so make sure you get that right. Okay, guys, any questions for today? Okay, so very simple. I just want you to finish off the MCQs. Right, we go through them next week. Right, but of course, bring this along next week. Yep, that's all for today. Hey, bye. Yes, bye bye.
I'm not coming next week.
Next week, I thought it's 16. Next week or 16?
Next week.
Next week,
Yeah.
not 16. Oh, okay, now that I do recording for you.
Okay.
You can't join online also, right?
Yeah.
Can
Yeah.
Okay.
I going to other country.
Oh, good. Okay, I record for you then. Bye bye. Yes, hello. Yeah.
Finish Oh, it's already man. So we can get
Before you correct. They keep carrying the banging and all that. So if you want to talk the story, especially if your wall is supposed to sit down and you keep saying, no, it's not enough.
Since you already done already, since I wrote down the conclusion.
I'm too dressed to go and play my. And it's speaking. Those you guys. Okay, do your homework.
Okay. What's that?
Very lively class, huh?
Yeah, I think it was like that. At least stayed silent for longer periods of time. I was very proud of it.
What did you do to them?
Huh?
What
I
did you
think
do?
it's more like not letting them push them, just like film and then you don't perform.